Landing on the moon remains an extraordinary challenge, even with decades of technological advancements. Just this year, the first two American lunar landing attempts since Apollo 17 in 1972 ended in failure. Astrobotic's Peregrine lander never reached the moon due to a propellant leak, and a month later, Intuitive Machines' lunar lander tipped over during its final descent. The lander relied on an autonomous visual guidance system, but a landing leg struck a rock the system failed to detect, causing it to break and the lander to fall on its side. Despite this setback, the mission returned valuable data to Earth, though losing a $120 million lander was a significant blow. These failures highlight a critical need for NASA to relearn and refine the technologies required to land on the moon reliably. Why, even with modern advancements, is lunar landing so difficult? Firefly Aerospace's Blue Ghost mission, set to launch in January, aims to address these challenges. A visit to their Austin, Texas headquarters offered insight into how they're designing Blue Ghost to maximize success and make lunar landings more achievable for future missions. The difficulty of lunar landings can be traced back to the Apollo era. During Apollo 11, Houston communicated with Michael Collins in lunar orbit, asking him to relay messages to Buzz Aldrin inside the lunar lander. Static from a poor connection with the command module posed a problem. Aldrin manually adjusted the lander's antenna to improve the signal. Without this fix, the landing might have been aborted, as losing contact with astronauts on the surface was unacceptable. Today's lunar missions, like those under NASA's Commercial Lunar Payload Services (CLPS) initiative, operate without a command module or human pilots. These missions, funded by a $2.6 billion pool, involve private companies like Intuitive Machines, Astrobotic, and Firefly, each receiving roughly $100 million per mission. Sending humans is impractical for these exploratory missions due to cost. Launching a kilogram of payload to the moon costs about $1 million. The two spacesuits worn during Apollo 11 weighed 160 kilograms alone, and supporting human life along with ensuring their safe return exceeds NASA's current budget for these missions. Historically, lunar landings have a high failure rate. About 50% of all moon landings across spacefaring nations fail, and 55% of Mars landings fail. These odds are unacceptable for human missions, making robotic missions critical for developing reliable landing technologies. These missions test autonomous systems and pave the way for crewed missions under NASA's Artemis program. While technology has advanced, landing a lunar lander for $120 million was unimaginable in 1972. Challenges persist. During Apollo 11, Neil Armstrong made multiple course corrections to avoid unexpected boulders and craters. Today, the Lunar Reconnaissance Orbiter, LRO, provides a detailed 3D map of the moon at 100-meter resolution, with even higher resolution for key areas. This map enables autonomous navigation by allowing landers to compare camera images with known surface features like craters. At Firefly's headquarters, Chief Engineer Will Coogan showcased Blue Ghost's vision navigation system in the clean room where the lander is being built. The system uses two cameras, one angled to view the lunar surface during the braking phase, when the lander slows its horizontal velocity, and another pointed downward for the final descent when the lander fights gravity. The downward-facing camera is mounted on a bracket to avoid interference from glint off the lander's legs, which could disrupt navigation. The cameras feed into an extended Kalman filter, integrating data from other sensors. However, there's no direct redundancy for the cameras themselves, making their performance critical. Blue Ghost relies on the LRO's map to determine its position by matching camera images to known craters. Since the moon lacks weather, features remain stable, though the system must account for changing shadows. Blue Ghost will land along the moon's terminator line, the boundary between day and night at lunar sunrise, giving it 14 Earth days of operation before the lunar night's freezing temperatures, as low as -130 degrees Celsius, render the lander's batteries and electronics inoperable. The Vision navigation system operates similarly to star trackers used for spacecraft orientation, but stars can't provide position data across the solar system. With the moon's craters mapped precisely, the system calculates altitude, orientation, position, and velocity with high accuracy. However, at lower altitudes, challenges arise. During Apollo 11, dust kicked up by thrusters obscured Armstrong's view, a problem that still affects autonomous systems. Below a certain altitude, the LRO's map lacks sufficient resolution for visual navigation. Coogan explained that at this point, the lander relies on features identified earlier in the descent, using a simultaneous localization and mapping SLAM algorithm originally developed for robotics. This algorithm tracks new features relative to known ones, allowing navigation as the lander approaches the surface. At about 10 meters above the surface, dust plumes obscure the cameras, rendering visual navigation unreliable. The lander then depends on its inertial measurement unit, IMU, for a soft landing. Precision thrust control is achieved through the Spectre reaction control system, which uses 8 hypergolic rocket motors. Lunar landers are lightweight, with much of their mass dedicated to propellant. As propellant is consumed, the lander's thrust-to-weight ratio and center of gravity shift continuously. Intuitive Machines lander stacked its propellant tanks vertically to avoid lateral shifts, but this raised the center of gravity, contributing to its tip-over. Blue Ghost uses 4 side-by-side tanks to lower the center of gravity and maintain balance, as the two propellants have different densities. The reaction control system adjusts thrust through duty cycling, turning engines on and off to maintain precise control. The lander's legs are also engineered for stability. Coogan highlighted their design, which includes 3D printed titanium cylinders with crushable aluminum honeycomb to absorb landing impact. This ensures all 4 feet contact the ground, even on uneven terrain, preventing instability. Each leg has a swivel ankle to avoid catching on the surface and a sensor to detect landing by registering when the foot flattens. These sensors, combined with data link signals, engine status, and IMU orientation, help confirm a successful landing. However, a scenario exists where these indicators could falsely suggest success if the lander bounces and is in freefall. The moon's distance from Earth limits real-time data, complicating landing confirmation. Communication and navigation systems are another hurdle. The US and Europe lack robust lunar communication infrastructure, unlike China, which launched a relay satellite to Lagrange Point 2 in 2018. This satellite enables communication with the moon's far side, supporting China's 2019 far side landing and a 2024 relay with a parabolic antenna for multiple probes. The U.S. relies on NASA's Deep Space Network for interplanetary navigation, but Blue Ghost will test using GPS signals from American and European satellites for lunar navigation. This could provide accurate position, velocity, and time data. NASA's LunaNet initiative aims to build a network of lunar nodes and satellites, starting with Intuitive Machines' Lunar Node 1 beacon, which transmitted briefly after its lander's failed landing. Blue Ghost's second mission in 2026 will carry a European Space Agency communication satellite to support polar and far-side missions. These CLPS missions are critical for developing lunar infrastructure, making landing safer and more reliable. Like the Apollo program, which faced failures before its successes, these missions are a modern, cost-effective equivalent. They test and refine technologies at a fraction of Apollo's cost, paving the way for Artemis and future exploration. Beyond the technical discussion, it's worth noting the broader context of supporting educational content about space exploration. Platforms like Nebula provide a stable alternative to volatile YouTube ad revenue, enabling creators to produce high-quality content. For $3 a month, Nebula offers ad-free access to exclusive programming, including detailed recreations like the Battle of Britain Command Room, which required extensive research and 3D animation. Lifetime memberships are available for $300, and gift cards or guest passes allow users to explore the platform without commitment. This support allows creators to focus on storytelling rather than algorithms, ensuring projects like in-depth lunar mission analyses can continue. In summary, landing on the moon is fraught with challenges, from autonomous navigation and dust interference to precise thrust control and communication limitations. Blue Ghost's design its cameras, low center of gravity, and shock-absorbing legs aims to address these issues. By testing new navigation and communication systems, Blue Ghost and other CLPS missions are building the foundation for reliable lunar landings, bringing humanity closer to a sustainable presence on the Moon.